So this is, of course, not going to be a real group, because what we'll do is that we'll take two different waves with slightly different phase velocities. So suppose we have psi1. Psi1 is a sine of kx minus omega t. And then we have psi2, which has the same amplitude a, and I'm doing this for simplification. Sine of k plus, say, delta k x minus omega plus delta omega t. So delta k and delta omega are small. So so the phase velocities of the, of say psi1 is given by, or the velocity. I mean, if I look at this wave, it has only one velocity. Is the phase velocity is the same as the group velocity. Is given by omega k, and v2 is given by omega plus delta omega divided by k plus delta k. Now, if I look at the superposition of these two waves, psi is equal to psi1 plus psi2, the simplest superposition that I can do, then I can use, using the, trigonometric identity that sine of c plus d plus sine of c minus d is equal to 2 sine c cosine d. Then by doing this, we find that psi, which is given by psi1 plus psi2, is 2a sine of k plus delta k by 2 x minus omega plus delta omega by 2 t times cosine of delta k by 2 x minus delta omega by 2 t. Okay? So what does this look like? So this mathematics should be familiar to you if you have studied beat. Do you remember beat from waves and vibrations?
The difference of frequency.
Yeah. When you have two, when you have two sounds which are close to each other, then what you get is that you get, as a result, a sound which has a very high, which has a frequency, which is, has a high frequency, but the amplitude of the frequency, changes with time. But the just one second, okay? Hello? Sorry about that. Okay, you guys still there?
Yes.
Yes, sir.
Okay. So, what does this look like? It looks like this. The wave that's propagating looks like this. Okay. So there's a, so this is the, the frequency and the wavelength, which is high. So it's given by these guys. But the envelope there's also a frequency and a wavelength. And those are given by these guys. Okay. So it's the velocity of the envelope which is the group velocity. So let's write that down. The other one is the phase velocity. Okay. So as you add more and more frequencies, you will see that only one or two of these envelopes, you will basically get a bona fide wave packet. Okay. But you'll still get these sort of these phases. So the phase velocity v phase is going to be, if I look at this, it's omega plus delta omega by 2 divided by k plus delta k by 2, and the group velocity is delta omega by delta k. Now, in the limit in which delta omega goes to 0 and delta k goes to 0, the phase velocity just becomes omega over k, which can be any old number, whereas the group velocity becomes d of omega d of k. Okay, and this is the important relationship about the group velocity that I wanted to derive. Okay, and you can see that these two are not necessarily the same. Okay, so this is the definition of a group velocity. Now, any questions?